Greetings, everyone. It's a little after 1 p.m. Eastern Time, and that means it's time to begin another CoCoRaHS Weather Talk webinar. Hello, I'm your host, Henry Regis, and along with me today is CoCoRaHS National Director, Nolan Duskin. Running things behind the scenes today is Noah Newman and Zach Schwalbe. We're coming to you live from the CoCoRaHS Center here at the Colorado Climate Center in Colorado State University in beautiful Fort Collins, Colorado. And we're so glad you can join us for the next hour and 15 minutes. Today we bring you the fourth episode in our Weather Talk webinar series titled Understanding and Identifying Clouds. Today's webinar is being recorded and it will be available on the CoCoRaHS website for future viewing. Each of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. After our speaker's presentation today, we will open up the webinar for questions from our audience, which our presenter will answer live on the air. With us today in our studio is Tom Schlatter from Boulder, Colorado. Tom, a lifelong avid weather watcher and longtime friend of CoCoRaHS, is now a retired volunteer at NOAA's Earth System Research Lab in Boulder, Colorado. Some of you out there will also recognize Tom's name from WeatherWise magazine, where he's been writing the Weather Queries column for the past 31 years. Welcome, Tom. It's great to have you with us today.
Thanks, Henry. And Tom, this is Nolan Duskin, and we're sure glad you're here today. We're looking forward to this.
And Tom's presentation should be coming up here shortly on the screen.
There we go.
Okay, great.
Well, if you're on the far side of 50 years old, as I am, you maybe remember a song composed by Joni Mitchell in 1967. Both Sides Now. Judy Collins made it a big hit in 1968. Here's how it starts. Bows and flows of angel hair, and ice cream castles in the air, and feathered canyons everywhere. I've looked at clouds that way. We've all looked at clouds, I think, in a whimsical, childlike way. But for many of us, the last line of this first verse might apply. I really don't know clouds at all. Well, if that applies to you, you have come to the right place today. What you've got on the screen now is kind of an outline of where we're going to be going. We'll first talk about how clouds form and disappear. That involves condensation and evaporation. And then we'll make use of 5 words with Latin roots for naming clouds. In fact, that answers one of the questions we asked you when you first registered for this webinar. How many words with Latin roots does it take to name the 10 most basic cloud types that we'll be discussing today? The answer is 5. Then we will identify the 10 basic cloud types with lots of pictures. And we'll see how thunderstorm clouds can grow so tall. What makes that happen? And then in about 40 minutes from now, we'll have a quiz. Not to worry about the quiz. All answers are anonymous. All we do is count the number of answers that you give, and then we'll discuss the answer one by one. And we finish up with a question and answer session. So let's get started. This first part, by the way, is challenging for a lot of people. So if you can hang with it, you're going to learn a lot in the next few minutes before we start looking at cloud pictures. But this preliminary information, I think, will be essential for you to understand how clouds form and die out. Now, if no clouds are present, if we're dealing with a volume of air that has no cloud particles in it, then the following principles apply. If I take a volume of air in this blue box and I force it to rise, it will cool at a rate of about 5.4 degrees Fahrenheit per 1,000 feet of ascent. Now in metric units, the numbers are very easy to remember. It's about 1 degree Celsius per 100 meters of lift. So rising air cools at this rate. This is a very special rate, and it applies throughout the atmosphere. Similarly, come over here to another air parcel, or volume. If I force that air down, it will warm up by compression at the rate of about 1 degree Celsius per 100 meters, or 5.4 degrees Fahrenheit per 1,000 feet of forced descent. But of course, the atmosphere contains more than just dry air. After oxygen, the most important atmospheric gas is water vapor. If we didn't have any water vapor in the atmosphere, there would be no clouds, no weather, no precipitation, and ultimately no life at all, same as oxygen. Here's an important fact to remember. The amount of water vapor in the air is limited by temperature alone. The higher the temperature, the more water vapor can exist in air. Now this has very important consequences. If the air cools and the amount of vapor in that air is kept constant, the relative humidity rises. If the air cools enough, the humidity reaches a maximum value, which, as you know, is 100%. And then water vapor in the air begins to condense into a cloud or into fog. If cooling continues still further, there will be more vapor condensing, and the humidity stays at 100%. But the more and more vapor that condenses, the more and more cloud particles, tiny droplets, that you have. So, rising air makes clouds. Why is that? Because when you force the air upward, the relative humidity contained in that volume of rising air goes higher and higher until it hits 100%, and then condensation occurs and a cloud forms. Let's talk about the other end of the spectrum. If foggy or cloudy air warms up, some of the droplets will evaporate. Why is that? Because the more you warm the air, the more vapor can be in that air. So if you've got cloudy air and you start warming it up, some of the cloud particles will begin to evaporate, and as long as there's still water droplets or ice crystals in that volume of air, the humidity will stay close to 100%. But if you apply eventually enough heat to that parcel, all the droplets will evaporate, the cloud disappears, and at that point, then the humidity starts to drop. So sinking air destroys clouds, rising air makes clouds. Let's put some of these facts to work. Now this and one of the next slides I'll show you are the most challenging in this whole talk. So if I don't get through the first time, you can ask a question about it and we can revisit it after I'm done, when we get to the question and answer session. So let's now go back to where we began and just talk about a volume of air that has perhaps some vapor in it, but definitely no cloud particles in it. No raindrops, no snow crystals. So we're talking about cloudless air. Now this is a diagram that shows height on the vertical axis and temperature on the horizontal axis. And the actual values along that axis doesn't really matter. I've got 5 yellow lines here, all parallel to each other. And these yellow lines go back to that special decrease of temperature with height that I mentioned in the beginning, when you take a dry air parcel and lift it or force it downwards. The temperature change in the vertical is about 5.4 degrees Fahrenheit per 1,000 feet of lift or forced descent. So we've got 4 different situations to consider here. The first one is unstable. Now the yellow lines always represent that special decrease of temperature with height, 5.4 degrees Fahrenheit per 1,000 feet. But the dashed red lines portray the measured temperature in the atmosphere. So I'm going to start by these red dots with an air parcel at a particular altitude in the atmosphere, and I am going to force this air parcel up. And as I follow the parcel, as we said before, it's going to cool along this line. But I'm comparing it all the time as I lift it to the measured temperature outside the parcel that I'm forcing aloft. And you see, in the unstable case, as soon as I raise this parcel up, it is warmer on the temperature scale. Here's the temperature scale. It's warmer than its surroundings. And so what does it do? It'll rise like a hot air balloon. In fact, it will accelerate away from the starting position along this line. Similarly, if I force the parcel down, it immediately becomes cooler. It lies to the left of the environment temperature, and it becomes more dense than its surroundings, and it accelerates downward away from this point. That's why it's unstable. If I move an air parcel up or down, it accelerates away from its starting position. Now take the neutral case. In this case, the decrease of temperature with height as measured in the atmosphere matches the increase or decrease of an air parcel if I force it up or down. So now if I force it up, I compare it at every altitude with the temperature of its surroundings, and they're the same. So if I give it a little nudge this way, it can just keep going, but it's not going to accelerate. Similarly, if I push it down, it'll keep the same temperature as its surroundings, and it'll keep going down, but it won't accelerate. So this is called the neutral case, and when we have this realized in the atmosphere, as occurs on summer afternoons very often, vertical mixing of air is easy to accomplish because the parcels of air that are being pushed up or down have the same temperature as the surroundings. Now let's go to the stable case. Here, if I raise the temperature, if I push the air parcel up just a little bit, it immediately becomes cooler than its surroundings. That's the red dashed line. So it's more dense, and that air wants to come back to where I started. If I push it down, it becomes warmer than its surroundings, less dense, and it wants to go back up to where I started it. That's the stable case. Now there's an even more stable case which occurs when there's an inversion. With an inversion for a thin layer depicted here where I start my parcel, I've got an increase of temperature with height. So as soon as I move that parcel in either direction, up or down, that air is going to want to come right back to where it started very quickly. So vertical motions are inhibited in the stable case, and they're just kind of stopped dead in the very stable case, common in the early morning when you have an inversion fairly close to the ground. Now, let's go back again. Well, let's go to the next one first, and then we'll move back. What happens when water vapor gets involved in all this is a little more complicated, because when you start condensing vapor, that liberates energy into the air. In fact, it raises the temperature. By contrast, when evaporation occurs, if I evaporate cloud droplets or ice crystals, that takes energy out of the air, and it lowers the temperature. Melting of snowflakes does the same thing. That takes energy out of the air, and it lowers the temperature. So that's the principle of latent heating and cooling. Now we're going to back up to where we were a moment ago and apply that information to the neutral case. So now I'm going to lift a parcel, and as I lift it, it's going to follow the yellow line. Temperature is the same as outside the air parcel that's being lifted, but the humidity is rising because I've got vapor in this parcel, and at some point, let's say here, condensation begins to occur within this parcel. Well, it's not going to follow the yellow line anymore. It's going to follow a line that lies to the right of the yellow line, because as we said, when condensation begins, that's when heat is imparted to the air parcel, and its temperature will be higher than it would be if no condensation were occurring. So now that parcel is going to follow a trajectory more like this, because heat is being released from condensation. What that means is my parcel, which would have been neutral, is going to become buoyant because of the condensation within it, and that means it's going to be able to rise on its own, a lot like what happened over here. This is the toughest thing to understand, but if you get this, you're going to understand an awful lot about tall clouds and how thunderstorms form. Now we've got two axes here. As before, we have got altitude in the above sea level. Over here in kilometers, we've got it over here on the right side in thousands of feet. The horizontal axis is temperature. If you like Celsius, you can look at the labels at the bottom, or if you like Fahrenheit, you can look at the labels on the top. So let's go down here to the bottom at the ground, and first we'll talk about the red curve and the blue curve. Let's say we have a balloon with instruments attached that measure the amount of moisture in the air with altitude and measure the temperature as the balloon rises through the atmosphere. And I can plot the measured temperature and the measured dew point, a measure of humidity, on this graph. And we've done that. Red curve's temperature, blue curve is dew point. But I want to follow, let's say it's 3 o'clock in the afternoon, and I want to follow an air parcel that starts from the ground at this temperature and with this dew point, a measured amount of humidity in the parcel. As we've said several times already, the parcel starts out cooling at the rate of 5.4 degrees per 1,000 feet of lift. I'm forcing this parcel up. We don't have time to discuss how air volumes can be forced up from low in the atmosphere, but let's just say we're making it rise. The humidity is rising as I lift the parcel, and eventually it becomes 100% right here. This is when condensation starts to occur, and that's where the cloud base is. Now, once condensation begins to occur, the parcel does not cool off at that same rate, but at a lesser rate. Notice, all through here, my parcel is cooler than its surroundings, so I have to keep pushing it up if I want to get to this point where the temperature inside the rising air volume is the same as its surroundings. But because condensation is going on here, look what happens. From this point all the way up to here, that's probably 30,000 feet, my air parcel is warmer than its surroundings, and so it can rise on its own. That's what makes thunderstorms. That makes what makes these bulging, billowy clouds boil up in the atmosphere and form a thunderstorm. Finally, and this relates to the shape of the cloud, you'll see the boiling, bubbling part here, but at the top of a thunderstorm, when it forms, we get an anvil shape. Why is that? Well, when the updraft reaches this point near the top of what's called the troposphere, where all our clouds and weather occur, the parcel again becomes colder than its environment, more dense, and so the updraft slows down and it kind of spreads out as if it had hit a lid, and that's when the anvil forms at the top of the thunder shower and spreads laterally. That spreading occurs above this point where the air parcels become more dense than the surroundings. So this was a bit much to swallow, I know, in a short time, and if you wish, with questions, we can come back to it a little bit later. But armed with this information, we're ready to talk about how we name clouds and what they look like. So, we've already said all you need is 5 different words to name the 10 most basic kind of clouds. And stratus comes from a Latin word that means layer. Whenever a cloud looks like a sheet, or if it's in a layer, we attach the word stratus to it. And that answers another question that we had on the little test that you had when you registered for this. Sheet-like clouds have what word incorporated in their name? The answer is stratus. And by golly, more than 90% of you answered that question correctly. Congratulations. Another word we use to identify clouds is cumulus, meaning a lump or pile, from the Latin word. Then there's the word alto, which comes from the Latin word altus, which means high. So to jump ahead just slightly, if I put alto together with cumulus, I get altocumulus, which means a high cumulus cloud, and that's in the parlance adopted by the World Meteorological Organization. Altocumulus clouds are at mid-levels. They're generally speaking from 8 to 20,000 feet high. And then cirrus. Cirrus comes from a Latin word meaning curly or wispy or fibrous, and that's the word we use for all ice crystal clouds. And then finally we use a Latin word for rain, nimbus. So by putting these 5 words, root words, together in combination, we can name 3 of the basic low-level clouds, 2 of the mid-level clouds, 3 high-level clouds, all composed of ice, and 2 precipitating clouds that have rain or snow falling from them. And those are stratus, cumulus, stratocumulus, altocumulus, altostratus at mid-levels, cirrus, cirrostratus, cirrocumulus, nimbostratus, and cumulonimbus. Now let's look at some photos of all 10 of those clouds. So we'll start with clouds that have little vertical development. They are more or less flat clouds. We'll start at the bottom with stratus. This is a stratus cloud on the ground. It reaches all the way down to the ground. It's fairly thick because you can't see the sky through it, but you can see it's lowering the visibility at the surface. So stratus pertains to a low cloud that is featureless, amorphous, can't see any details when you look at the cloud. Here's a view of stratus that's not on the ground, but it's just about 1,000 feet above the camera, and it's covering these foothills here. Here's a view of stratus clouds from above. Sometimes stratus clouds are fairly thin and you can see the sun through them, but in every case they are low, either close to the ground, or if they touch the ground, they're causing fog as well. Then we go to another form of low cloud, reasonably low, a few thousand feet above the ground, cumulus. Notice how they are lumpy. They are flatter. They are fairly flat clouds. They are wider than they are tall, and they are more or less randomly distributed across the sky. So if you have a lumpy cloud like this, and the lumps are large, namely the clouds fairly close to the ground within the first few thousand feet, we call them cumulus. Here's another example of cumulus clouds. And here's an example of cumulus clouds as viewed from above. Sometimes they can organize into streets. You can see something like a street or a row of these cumulus clouds here. But more often than not, their distribution is totally random. That's what cumulus clouds look like from above, little lumps. Then we get stratocumulus. When cumulus clouds become numerous enough, they may spread and merge into what we call stratocumulus clouds. A lumpy cloud, big lumps, but the word stratos attached because they are forming a layer like this. Here's another example of stratocumulus clouds. Sometimes they look like rolls, but in every case with stratocumulus, the lumps are really big, and they are forming a layer of clouds. Here is a cloud that is giving precipitation. These clouds are pretty much featureless. You can make out a few details, but not much, and you can see precipitation falling. Well, if a cloud is precipitating, we call it nimbostratus. Nimbo for rain, or it could be applied to snow as well. Here's another example of nimbostratus. You might be able to see a few snowflakes between the camera and the shutters here, which is a dark surface. So it was precipitating here. You can see visibility is reduced by at the silo back here by snow. So we call this nimbostratus 2, a featureless cloud that is precipitating. Now we move to the mid-level clouds. This is a lumpy cloud, alto cumulus. Sometimes they form a layer like this. Sometimes they're detached like over here, but we call both of them alto cumulus or high cumulus. Here's another example of alto cumulus. Lots of times they form in waves. And by the way, alto cumulus are responsible for a lot of really beautiful and spectacular sunsets. But these are alto cumulus clouds now. How do you know it's alto instead of just plain cumulus? Because the lumps aren't as big as they are with pure cumulus clouds, which are closer to the ground. Then we have a mid-level cloud called altostratus. This is a sheet-like cloud. It's in a layer. You can tell it's fairly high because this big peak here is 3,000 feet above the neighborhood where the photo was taken, and it's featureless. So altostratus, a mid-level cloud that appears like a sheet. Here's another altostratus cloud with some lower clouds in the foreground, but you can see the sheet-like character of the altostratus cloud, which is higher up than these low clouds, and it is blocking out the sun, giving it kind of a watery, filmy appearance. Altostratus. Then we get to some of the more beautiful clouds, cirrus. These are fibrous, filmy, thin. You can often see blue through them, and they've got lots of beautiful detail in them, kind of like snowflakes. But these are ice crystal clouds, and it's this character, this filmy, fibrous appearance that gives away the fact that they are composed of ice crystals. Cirrus clouds. Here's cirrus clouds covering more of the sky, but still not covering it like a sheet, I don't think. And so we call this cirrus clouds as well. Here is a tip-off that you are looking at an ice cloud. If it's fibrous, and like this, and it has colors in it, by the way, this is a telephoto lens photo, that is a tip-off that it's an ice cloud. This is refraction of sunlight that results in the colored cloud. You will see these as sundogs to the right or left of the sun, generally speaking only early and late in the day. But if you see the colors, you know for sure that is an ice cloud. And then when cirrus cover the whole sky in a white sheet like this, sometimes pretty thin, you can see blue through them, this is cirrostratus, a sheet-like cloud made of ice crystals, and the tip-off is these are filmy, fibrous-looking clouds. Here is a very thin layer of cirrostratus. Look at that. There's a halo around the sun. This is at a distance, angular distance of about 22 degrees from the sun. The sun is hidden down here by these statues, so we could see something and not be blinded. But whenever you see colors in a cirrus cloud, either a ring or those sundogs I showed you earlier, you can be sure it is a cirrus cloud. Now, if you see a ring around the sun, it's probably a cirrostratus because it takes a sheet-like cloud to be able to see the whole ring. And finally, cirrocumulus. These are very high, lumpy clouds. The lumps are very small, and that's the tip-off if the cloud is very high, but you can also see the fibrous appearance that is characteristic of cirrus clouds. And so when we see tiny lumps of cloud, sometimes looking like rippled sand, and sometimes with waves in them, tiny lumps, but still fibrous, we call them cirrocumulus. I've got a few more pictures of these that you can see. See the tiny lumps? Here's cirrostratus with some waves, cirrocumulus, excuse me, with lumps and waves in it, like rippled sand. And finally, one more picture of the cirrocumulus clouds. We still haven't talked about One more thing before we go to clouds with big vertical development. Contrails, we're all familiar with this. Sometimes if the humidity in the high atmosphere is high and a jet aircraft at 30,000, 40,000 feet flies through this air, the vapor in the exhaust from the jet aircraft creates a cloud. It's adding vapor to very cold air that had high humidity. The humidity becomes 100% and you get a condensation trail, contrails for short, which makes these streaks in the sky. And these coexist very commonly with natural cirrus clouds. Now we get to clouds with strong vertical development. These clouds are taller than they are wide. Sometimes on a summer afternoon when it's hot and sticky, the fair weather cumulus clouds that we saw before start growing vertically. And when they get taller than they are wide, they might appear like this. The bases become dark and the tops start to tower, and you see these cauliflower-like shapes. Those are just called simply towering cumulus. That's what you'd call it if nobody even asked you to name the cloud, towering cumulus. Here's another towering cumulus, very clearly taller than it is wide. This is the case when the air gets unstable because of the condensation of moisture in the air parcels that are being lifted in the updraft through this cloud. Well, if you carry this to the logical conclusion, this cloud is going to hit the top of the troposphere. That's the lower part of the atmosphere where most of our clouds and weather occurs. And when that happens, as we mentioned before, the updraft can't go any higher, so it has to spread out like this, and it's forming an anvil at the top here. You can see another cell growing to the left of this one, which has an updraft, and it reached the same level, and it's starting to spread out laterally too in the shape of an anvil. These clouds are tall enough to produce rain and other nasty things out the bottom, and lightning and thunder. So if we have a cloud tall enough to produce lightning and thunder and rain, we call it cumulonimbus. And this anvil shape at the top is definitive for identifying cumulonimbus. Here is a monster cumulonimbus, which is spread out at the top. You can see all these cauliflower-like appendages. Here's a big updraft over here, and looks like there's another one starting on this side of the cloud too. But this is a monster cumulonimbus cloud, probably one that was producing severe weather. Here is a cumulonimbus cloud as viewed from 30 to 40,000 feet from a jet aircraft, and you can easily see the spreading caused by the anvil. This little dome here poking up out of the top of the anvil is the top of a very vigorous updraft which temporarily poked through the top. Sometimes very strong updrafts can do this, but then they sink back down into the anvil. But if you see something like this, you know it's a very, very strong updraft because it was able to poke through the top of the anvil, at least temporarily. I thought you might like to see a couple of things that result from really big cumulonimbus clouds. This was a blowdown of a good portion of a forest in Michigan. It says quaking aspen, but it should really say croaking aspen, because this isn't an earthen embankment here. It's just uprooted trees which fell away from the camera. And you can see, you wouldn't have been able to see sky before the storm roared through here. But most of the trees were either split or broken or uprooted. Another problem we have with big thunderstorms is lots of hail. This is a sample of a hailstorm that fell in my hometown of Boulder, Colorado just a couple summers ago. So, not to worry, this is a self-test, and we're going to go through these photos one at a time. And I'd just like you to vote, as it were. Again, we don't keep track of individuals. We're just going to count the answers and see how you did. I'm going to show you some photos of clouds, just like the ones we saw. Well, maybe not just like, but at least similar to the ones we saw. And you put down your answer. So Here's the first one. Remember now those 5 words that we're using to identify clouds. Is it lumpy? Is it sheet-like? Are the lumps big? Are the lumps small? Can we see colors in the clouds, as in cirrus clouds? So just keep those 5 words in mind. And I'm giving you 5 choices here on each slide. So see what you think this is. And we'll wait a couple seconds for you to look at them, and then you'll be able to vote. This is the first time we've tried showing the votes on the screen, and we'll see what we get. We hope it works. Okay, 57% said altocumulus, and you guys are right on with that. Remember we said altocumulus, medium-sized lumps, so that's the high cumulus part, and beautiful sunsets. So let's go on to the next one. Well, the sun is hidden by this transformer on the pole here, and you got 5 choices: stratus, stratocumulus, altostratus, cirrostratus, nimbostratus. So we'll give you a few seconds to decide what you think this should be. Is it lumpy? Is it sheet-like? If it's sheet-like, is it a high cloud? Is it a low cloud? We'll see what you think. Votes are coming in. Wow, you're getting better at this. 75% of you, fully 3/4, said it was cirrostratus. Why is it cirrostratus, and how do you know it's cirrostratus and not altostratus? Because if you look really closely, right here, you can see a ring around the sun. That's a halo. And when we see that, we know there has to be an ice crystal cloud there that made the ring visible. And that's why we call it cirrostratus and not something else. Number 3. Looks like a nice day to me. So are we looking at cumulus, stratocumulus, altocumulus, cirrus, or cumulonimbus? We'll give you a few seconds to decide. Okay, here come the results. Very good. 70% said cumulus. Why? Big lumps, but more or less random distribution in the sky. They are wider than they are tall, so we certainly wouldn't call them cumulonimbus. And we wouldn't call them cirrus because they're not fibrous. And we wouldn't call them altocumulus because these are really big lumps. If they were smaller lumps, they'd be higher in the sky, and we might call them altocumulus. And finally, we wouldn't call them stratocumulus because they haven't merged into a complete layer yet. Here's one I bet you'll get. This is a big TV tower here, and I'll give you a big hairy clue. You can't see the top of it. So is it nimbostratus, stratocumulus, altostratus, cirrostratus, or stratus? I thought you'd do pretty well here. 63% of you said stratus, and you're absolutely right. Remember, if we call it stratus, it's a very low cloud. And if this TV tower is covered up at the top, it has to be a very low cloud. And the reason we call it stratus is because it's in a layer and it's sheet-like. There are no features at all visible in this. It's just a gray sky. That's all we can say. And we know it's low clouds. That's why we call it stratus.
But if there was some precipitation falling, then it might have been a nimbostratus?
Yes, it would have been nimbostratus. If there had been drizzle or something else falling, it would have been nimbostratus. Well, I see we got nimbostratus as one choice on this next one. But take a look at this. Try and decide if it's sheet-like or lumpy, if it's in a layer or detached clouds. And I'll tell you, it wasn't raining or snowing here. That's a clue. See what you think. Stratocumulus. Very good. 69% of you said stratocumulus, and that's the correct answer. Again, lumpy clouds, huge lumps, but they've merged to form a layer, and that's why we call it stratocumulus. All right. Is it lumpy? Is it sheet-like? You can see the sun weakly shining through. Nice winter scene. But what kind of cloud do you think this is? This one's a little tougher than most because it could be cirrostratus. We don't know for sure because there's no colored lights. If there had been any colored cloud in the sky, we would have said cirrostratus for sure. But I didn't give you that as one of the choices. So if you said altostratus, you were right on. It's sheet-like, no features visible, and cirrostratus wasn't one of the choices, so it really has to be altostratus. It's not a low cloud, it's not lumpy, and if it were cirrus, you would see individual filaments and blue sky in here, so it's not cirrus either. Altostratus is the right answer. I think you're going to do pretty well on this one too. Oh my, this is a vast majority said cirrus. It's plain cirrus. It's got wave-like patterns in it, but it's definitely filmy and fibrous. There's lots of blue sky, so we wouldn't want to call it cirrostratus. There are no lumps in it, so we wouldn't want to call it cirrocumulus. And the other two options are pretty much out. So, very good on that one. I can't imagine too many of you are going to miss on this one either. Just ask yourself a couple things. Is this a huge cloud? Is it tall or short? Is it higher than it is wide? Is it producing anything out the bottom? Well, if you said cumulus, you're not far off, but this is a monster cumulus, and it is producing rain, so we have to call it cumulonimbus. This is a really big cloud. It's big enough to produce thunder and lightning. So if you said cumulonimbus, you were in the majority, and you were dead on. If you said cumulus, don't feel bad, because it is a form of cumulus cloud. It's just a very big one that produces rain. Number 9. Maybe you can see against the red barn, there are tiny little white specks between the camera and the barn. It is snowing here, and that's a clue.
Tom, we've got someone from our audience that wanted to know if this is Cloud 9. He says his wife often says that he's on Cloud 9.
Yeah, this is Cloud 9. I didn't plan it that way, but I thank you for pointing that out.
And we won't be able to vote on this one. We only had 8 possibilities, so the folks will just have to check it off in their minds.
I'll go straight to the answer. This has to be nimbostratus, because we have a sheet-like cloud, and that means stratus, and nimbo because it's snowing. And let's go to the last one. I think you'll get this one too. Look at the lumps. Are they huge? Are they medium-sized? Or are they tiny? And can you see some fibrous things in here? Maybe like up in here and down in here. Cirrocumulus. That's the right answer here. Wouldn't call it cirrus because it's lumpy, or cirrostratus because it's lumpy. So it really has to be cirrocumulus. If they were huge lumps, it would be cirrus, but this is definitely a high cloud because the lumps are tiny. So for later viewing, when we won't have this interactive voting, we're just going to put the answers here, and if you come back and go through this again at your leisure, you'll see what the answers were. So that's pretty much it. And armed with the information in this webinar, I hope you'll start looking at clouds in a new way. In particular, I hope you'll look at clouds all day. So thanks for being with us, and I'll turn it back to Henry now, and we can do some question and answer.
Thanks, Tom. We really enjoyed that. What a great presentation. I'm going to ask the audience out there if they have any questions for Tom. If you'll go ahead and type them in, you'll see on your panel be a spot there that says questions, and we will take some questions for Tom. We'll try to answer as many as we can in the next 15 minutes or so, and then other ones we will try to get, if Tom has some time, to answer those online. So.
Tom, this is
offline. I'll answer you individually. If we can't get them, we can't get to them now, I'll try to answer them individually offline.
Tom, this is Nolan. When do you remember first being amazed and impressed by clouds?
Well, I think it was before I even knew what clouds were. It had to be elementary school or even earlier. That's what got me interested in weather, is just watching the sky. It was from the very beginning.
And that's the same as my experience. I can definitely remember even seeing anvils in distant thunderheads at sunset in central Illinois, and my parents said I wasn't even in grade school yet.
I remember as kids, we used to see animals in the clouds, animal shapes and stuff like that. We kind of lose that as we get older. Okay, we got some questions coming in, so let's go right away to these. Jim from Maine asked, what causes the various degrees of darkness in clouds? That's Bill, I'm sorry.
Okay. Generally speaking, it's the thickness of the cloud. Let's take the cloud that's on your screen now. That's a cumulonimbus cloud. We're up near anvil level. But you see, the deeper into the cloud you look, the top, very top here is very bright. The deeper into the cloud you get, the more sunlight is filtered, the more solar energy is absorbed. And so if you were at the bottom of this cloud looking up at its base, it would be very dark indeed. So the quick answer to your question is it's basically determined by the thickness of the cloud. The thicker the cloud, the more rain droplets or snow particles in that cloud, the darker it will be at the base.
Great. Here's one from Kerry in Albuquerque. He said, "Mammatus clouds developing sinking air beneath an anvil. Can you discuss that further? And also mountain wave clouds that develop in stable atmospheric environments." Excuse me.
Okay. You may have to repeat the second part of the question.
Sure.
Let me go back to the monster thunderstorm right here. You see these downward, right here at the bottom, you see upward bulging clouds, the cauliflower stuff, but there's upside down cauliflowers too, which we often see on the backside of thunderstorm anvils. These have a special word associated with them, mammatus, because they look like these pouches hanging down. These are downdrafts beneath the anvil, in most cases, that have cloud material in them. And when you see better examples than you can see here, I don't have any really good examples to show you, but if you see better examples in photos, these pouches hanging down are very smooth and have a very striking appearance. But they are caused by what are called saturated downdrafts. That is, cloud material that is sinking, usually on the underside of an anvil. And usually the air in these mammatus clouds is fairly stable. So if you flew an aircraft through them, you would not be bounced around appreciably. Now, if you flew in this, you would not want to fly in these mammatus, which are just forming here because it's too close to the thunderstorm updraft. But usually, the really good cases of mammatus that we see are well away from thunderstorm updrafts and usually seen most often on the backside.
Great. We've got another one here from Ruth in Maine. She wants to know why is the anvil not partially called stratus because the top is flat?
I don't know the answer to that. The top, if you look down at this from a satellite, or if you're in a very high-flying aircraft looking down, you would indeed see a fairly flat anvil with maybe an occasional bulge in it where an updraft poked up through temporarily. But that's a view that when cloud naming first started in the early 1800s, nobody ever could get. They're always looking up from the bottom. But the anvil name is commonly associated with these clouds, and they use a Latin word, incus, which is Latin for anvil. And from the very beginning, 200 years ago and more, those shapes have been identified as anvil shapes, and they mark the top of a thunderstorm.
Here's another one, Tom. Several folks have written this question. How do I guess the height of a cloud?
That's tough. If the cloud is more or less above you, and if it has lumps in it, I think the best way to guess is from the size of the lumps. So if it's low down and the lumps are really big, cumulus. If it's high cumulus, that's altocumulus. Those are from, say, 8 to 20,000 feet. And if you see very tiny cumulus, as in cirrocumulus, that's really high. For the sheet-like clouds, it's more difficult. For stratus, if you have tall towers near you, and the tops of tall towers or buildings in big metropolitan areas are covered, for example, in New York City or Chicago, places like that, happens pretty often, then it's a low cloud and you'd call it a stratus cloud. If you don't have hills, a few thousand feet high nearby, sometimes it's really very difficult to tell. One way is to look if you can see any features in a stratiform cloud, a cloud which has the word stratus in it. If you can see features in it, note how fast they move. If they're racing across the sky, then it's a low cloud. If they're moving more slowly, they're probably more distant. This assumes, of course, the same wind speed near the surface and very high up, which isn't always the case. But if they're moving more slowly, they're probably higher clouds. That's the best guidance I can give you, and it's pretty subjective.
Here's another question. If you could discuss lenticular clouds, if you've lived in the West, you've seen those, or in mountainous regions. When a mountain wave sets up, for example, what class are they in and how are they formed?
Yeah, I will. I wish I had a photo to show you, and I can't easily get to one. But lenticular clouds, or lens-shaped clouds, are not included in these 10 basic cloud forms that we've discussed here. But if you live near a mountainous terrain or very hilly terrain, even in the Appalachians, you will occasionally see clouds that have these very finely formed lens shapes. And if you watch them very closely, they are not moving with the wind. In fact, the air is flowing through them from the upwind side to the downwind side of the cloud. Now, why should that be? Well, the terrain over which the airflow has to go, it has to rise up over the terrain, that causes rising in air parcels that are crossing the mountains. And if the lift on the way up over the mountain crest is sufficient, as we said before, cooling causes the humidity in the air parcels to rise, and if the cooling is sufficient, condensation will occur, and then you get a wave cloud. The air has to be stable, though, over the mountaintop in order to form a wave cloud. So toward the peak of the lift, as the air crosses the crest of the terrain, you will get these smooth lens-shaped clouds. And then after the air has crossed the crest, it starts downhill again, and the cloud particles evaporate on the downwind side. And so that explains why the cloud doesn't move. It has to stay by the peak of the wave, near the crest of the wave in the atmosphere as the air blows over the crest.
Great. Here's one for Bob of Mississippi. He wants to know what causes the gray dinginess, basically the darkness and little bitty clouds, loners. The size does not seem to be a factor. So if you have a cumulus cloud, sometimes you get a real dark bottom or side to that.
Oh, boy. I don't think I know enough to answer that question, but I've noticed what you're talking about. You can put the same shape, a cloud with the same appearance in an otherwise clear sky, and they don't always look the same. The lighting is just different. Sometimes they appear darker, sometimes very thin clouds that have lots of blue sky around them appear gray more than white. I think it has to do with the lighting, whether the sky is a deep blue or whether there's pollution in it. I really can't answer that question because I don't know enough about atmospheric optics.
And I have heard some atmospheric, let's see, you don't call them obstetrician. What do you call them? Atmospheric opticians? No, I don't think I got the name right here. But folks that know how light moves through the atmosphere, and I've seen them talking about these same situations where what appears to be a little cumulus that should have a white top and a gray bottom is in fact all gray. And my recollection is that they said that sometimes it's by having less water content, less droplets in it, because not all clouds have the same concentration of
Nolan,
droplets.
you have turned on a light bulb in my brain, which isn't really fast right now. This is true. If you have a cloud, the same cloud, with a larger number of tiny droplets in it, as opposed to a smaller number of larger droplets with the same total water content in that cloud, the one with smaller droplets will definitely be brighter. So thanks for reminding of that. I had just forgotten.
Okay, Michael writes in and wants to know what clouds are referred to as scud clouds.
Okay, those are stratus clouds. They're close to the ground, and they're usually moving very fast across the sky. That's one reason they call them scud. But we call them fractostratus. That means wisps of stratus, or stratus clouds that have been broken apart, and you can see higher sky in between them. But usually they are driven by a strong or fairly strong low-level wind. Scud, or the technical name is fractostratus.
Tom from Massachusetts writes, what are the type of clouds caused by volcanoes? What are they called?
Okay, there is a lot of material in an erupting volcanic plume, and apart from the solid material in there, there's usually a lot of water vapor. And very frequently there's enough water vapor, and of course there's enough heat in the plume to form a very tall cloud, sometimes appearing a little like the cumulonimbus that you're looking at now on your screen. And sometimes you may have seen photographs of lightning produced by these very tall water droplet and ice crystal clouds, which ultimately, the source of that ultimately came from the throat of the volcano.
Speaking of lightning, Richard writes, can you make a couple of comments about lightning in clouds?
Yes. And in fact, that will allow me to answer the one question I don't think I talked about at all that you were supposed to answer when you registered for this, namely, what kind of stuff do you find inside of clouds? And I think your choices were water droplets, ice crystals, liquid droplets at temperatures below freezing, or snow crystals at temperatures above freezing. Well, in a thunderhead, you always have a mixture of liquid droplets, sometimes above freezing or higher in the cloud, what are called supercooled droplets, which can be well below freezing. They can exist at well below 0 Fahrenheit. It's a very common occurrence, not just in thunderclouds, but in all kinds of clouds. So you need liquid droplets, some of them at temperatures below freezing, and you need ice crystals. And all of those are present in a thundercloud. And they need to be present because that combination helps to separate charges of different sign, namely positive and negative charges, vertically within the cloud. And once the charge difference between these centers of positive and negative charges becomes great enough, the electric field builds up, and eventually a discharge can occur. Now, those discharges occur first inside the cloud, and you wouldn't even notice them. Even at night, you can hardly see them when the electrification eventually builds up. At the beginning of the formation of lightning, you might see a tiny little flicker at night. But ultimately, the charge separation goes far enough that you can get a large discharge, a stroke of lightning, sometimes coming out of the cloud and all the way to the ground. But it takes both solid and liquid precipitation and the particles having a different sizes in order to get this charge separation.
Phil from Florida writes, what type of clouds are noctilucent clouds?
Noctilucent clouds are a different class from those that we've discussed here. They may have water in them, or they may be clouds composed of tiny particles or droplets of acid. They appear very high in the atmosphere, either before sunrise or after sunset, and almost always in the coldest part of the entire atmosphere. There's something called the mesosphere, which is above the troposphere, and above that the stratosphere, then the mesosphere. And it's at the top of the mesosphere, usually in summertime, where the lowest temperatures observed anywhere in the atmosphere occur. And that is the place where at higher latitudes you sometimes see noctilucent clouds. And when you see them, I never have seen one myself, when you see them they are very striking because the rest of the sky appears fairly dark. And you'll often see them fairly low on the horizon as opposed to straight overhead.
Yeah, I remember.
Because they are still sunlit well after most of the rest of the atmosphere is in darkness.
I remember seeing them in Alaska, like at 3 or 4 in the morning up there. Tom, the height on those, how many thousand feet?
Oh gosh, I'm not sure, but it must be 80,000, 90,000. That's just ballpark, and I could be off by 50%.
Sure. Okay, we're going to take a couple more questions here. We've got a lot to go through. Do clouds form using dust or salt particles in the air? Writes Travis from Minnesota.
Very good question. To get condensation, when the relative humidity reaches 100%, we need cloud condensation nuclei. Those are tiny particles which will accept the condensation of vapor either into a liquid or into a snow crystal. In the case of the snow crystal, we need a special kind of condensation nucleus called a snow nucleus. Those can't be just about any kind of stuff that's floating up there in the form of pollution or natural aerosols. They have to be special. And you won't get a snow crystal forming unless you have an ice nucleus present in the atmosphere and the relative humidity very high. Won't happen. So the short answer to the question is we need nuclei in the atmosphere. These are tiny, tiny microscopic solid particles on which either tiny raindrops or tiny ice crystals can form.
Here's one from Roger in Valparaiso, Indiana, wants to know, do specific features such as large lakes, mountains, etc. create certain types of clouds?
Yes. We talked a bit earlier in the question and answer session about wave clouds, or clouds that look like lenses, lenticular clouds. And there the terrain, the flow of air over a ridge, is essential for creating that cloud. With regard to lakes, we can point to the Great Lakes as a good example, or the East Coast, off the East Coast of the U.S. in the wintertime. In the fall and early winter, let's deal with the Great Lakes. Before the lakes have frozen, the water cools down much more slowly than the air does as fall progresses into winter. And sometimes we'll get cold air masses with air much colder than the lake surface passing over. Well, there is a transfer of heat and moisture from the lake into the atmosphere when the temperature decrease with height is quite steep because of the cold air coming over the warm lake. And that will form these streets and broad swaths of cloud on the downwind side of the lakes and cause lots of snow shower activity or shower activity if the air is warmer along the Great Lakes. That's what causes the snow belts on the the downwind side. Let me be specific, the downwind side of the Great Lakes. If you look at satellite images, when a cold air mass moves off the Atlantic shore in winter, you'll see these streets forming just a few miles offshore and developing into cumuliform clouds that produce lots of shower and disturbed weather activity farther out into the ocean. So the answer is yes on both counts. Lakes and mountain ranges very much can affect cloud formation and weather.
We're going to take a few more. Steve writes, is it accurate that a ring around the sun or moon foretells precipitation?
It depends where you live. I'd say if you're in the Midwest or the East, it's probably a better indicator of precipitation on the way than it is out west, let's say from the Great Plains westward. What it does tell you unequivocally is if you see a ring around the moon, and it could be alpha-stratus or cirrostratus, or a ring around the sun, it tells you that there is a sheet-like cloud. And if you see that cloud thickening, then I'd say that's a trend maybe you want to pay attention to, because it could mean a warm front is on the way and the clouds will continue to thicken and eventually rain or snow will fall. But overall, it's not a very good sign, because quite often you can see those halos around the sun with cirrostratus clouds, and 8 times out of 10, 9 times out of 10, nothing happens in the next 24 hours. Not a very good indicator.
We're almost at quarter after the hour. We're going to take 2 more questions. Here's a combination one from 2 folks. One question was, what type of storms can you find tornadoes in? And then the other question was, on the picture which is on the screen, where would you look in this monster storm cloud for a developing funnel cloud? So two tornado type of questions.
Okay, what kind of cloud would a tornado form in? The answer is staring us in the face. That's a cumulonimbus cloud, a thundercloud. But where in this cloud would you be most likely to see the tornado? Well, you wouldn't see it from this view because you can't see beyond the edges of the cloud. The only way you can see the tornado is to look below the cloud base, which we can't see here. So I am guessing this was a severe thunderstorm merely because the convection, that is the updrafts, looks so vigorous. Whether there was a tornado in it, I have no idea. But if you have a weather radar, in particular a Doppler weather radar, and that radar shows that a portion of the thundercloud, usually on the south or southwest flank of it, is rotating, then you have to be very careful, because it's out of the rotating updraft type thunderstorms, which are reasonably unusual. Those are the ones that can spawn the larger tornadoes. Now, I would always look in the updraft portion of the cloud, which appears to be here on the right. You can see these bulging cumulus clouds underneath the anvil feeding up into the anvil. That's where you're most likely to find a tornado forming if there's rotation in the updraft in the first place. So it's generally speaking in the updraft part of the thunderstorm, and if the updraft is rotating, that's where the tornado will be if you're going to have one.
Okay, and for our final question of the day, and we've had several like this, Tom from Pennsylvania asks, why is the sky blue?
That has to do with the scattering of sunlight by the molecules in the atmosphere. Scattering is a redirection of, let's say, a ray of the sun, generally speaking in all directions. But the molecules in the atmosphere are of a size that is not greatly different from the wavelength of the incident sunlight. And under those conditions, there is a type of scattering called Rayleigh scattering, which is wavelength dependent. And the short wavelength end of the spectrum of sunlight is what scatters the most. And that's blue and purples. So the blue and purple end of the solar spectrum is being scattered substantially by sunlight, and all those air molecules are redirecting that sunlight toward our eyes from most parts of the sky, if the sky is clear. And that is why you see blue, because the long wavelength end of the spectrum, reds and oranges and yellows, are scattered much less.
Well, Tom, thank you so much. Tom will try to answer some of the other questions by email that we have on here. And we really appreciate you taking the time to be with us today, folks. I hope you've enjoyed the webinar. We're going to ask you, as you sign off today, to please take the survey at the end of today's webinar. And join us in a few weeks. We'll be doing a flash flood webinar on the 12th of April, led by Matt Kelsch. And he'll be talking about flash floods. We'll have more on that for sign-ups next week online with that. So once again, we'd like to say thanks for being with us, and we'll see you next time.
Thanks.